Section 15.1, vector fields. So to understand what a vector field is, what it looks like, how it's drawn, I highly recommend watching the Khan Academy video that I've included for this section. See Khan Academy video. I think they do a great job in that video of explaining kind of what a vector field is, how we sketch the vector field, where those vectors are coming from, and kind of what's going on there. So I think that's a great introduction. I think they can do a better job than I can with that. It's the link is in the same description, in the same attachment where this was. The link to this video was. Yeah, that was clear. I hope you understood what I just said there. Okay, so I'm going to spout some definitions at you, and then we're going to talk a little bit about that, maybe do an example or two. Okay? All right. So first, definition of a vector field. Okay, so a vector field over a plane region R is a function capital F, and it's a vector function. So in books and in print, it's going to be bolded. There we go. That assigns a vector f of xy to each point, each xy point in the region R. Okay, so every single point, you would plug in the xy value, you get a vector, that vector is assigned to that point. Okay, and like I said, the Khan Academy video I think does a great job of explaining kind of how that fits together and what it looks like on a graph. Okay, now the same thing, it can be ramped up into 3 dimensions. So in 3D, a vector field over a solid region Q in space, right, in 3 dimensions, is a function f. Again, it's a vector valued function of x, y, z. Oh, I'm sorry, I jumped ahead of myself. It's a function f that assigns a vector f of x, y, z to each point in that region, in that solid space Q, to each point in Q. Okay, so these come up all the time in physics. The gradient is a vector field. Let's write that down. The gradient of F is a vector field, right? You've got electromagnetic fields, you've got gravitational fields, you've got velocity fields. There's all kinds of fields, vector fields that come up in especially our physics courses, right? Okay, and we have some fields that are called conservative vector fields. And if a gradient, let's see, if a vector valued function f is a gradient of another function, right, then it's a conservative vector field. It's what we call a conservative vector field. And the reason they're called conservative vector fields is that the line integrals are going to come out the same regardless of the path that we take. And that's something that we'll talk about later on down the road. But that's the reason they're called conservative, and a gradient is such a vector field. Okay, so let's get that definition down here. So the definition, conservative vector field. Okay, so here's the textbook definition. A vector field F is called conservative if there exists a differentiable function f such that f is the gradient of f. That's the whole point. If our vector field is the gradient of some function, then it's a conservative vector field. Okay. Now that function f is called the potential function for f. F is called the potential function for the vector function f. So we need to be able to tell when a vector field is actually the gradient of some function. I forgot to put that on there. We need to know when this vector field is a gradient. So how do we know that? So suppose I'm given some function, some vector field, and it's equal to m in the I direction plus n in the j direction. And suppose I want to know, is this a gradient? Is this equal to the gradient of some little function f? Well, if it is, that f is equal to some function of xy, right? Then m is equal to the partial derivative of that function with respect to x. N is equal to the partial derivative of that function with respect to y. Yes? Okay. Now, if we have first derivatives, fx and fy, we can take the second derivative. So let's do the mixed derivative. So then this would imply that fxy would be equal to fyx, yes? So that's exactly correct. If we find, sorry guys, I'm stumbling over my own thoughts here. What I'm trying to get at is that we've got m equal to this f sub x, and we've got n equal to this f sub y. So we've got m is the partial derivative with respect to x, n is the partial derivative with respect to y. Such is the gradient. Well, the idea is if we took the partial derivative again, the second partial, we know that the mixed partials are going to be equal to each other. If we start with a function, we take the partial with x and the partial with y, then take the mixed partials, we'll get the same result on both of those. Okay, so what that means then is that if I were to take the partial derivative of m with respect to y, I'm going to get fxy. If I take the partial derivative of n with respect to x, we get fyx. Then if m with respect to y is equal to n with respect to x, we know that this came from some potential function f. It's a gradient vector field. If they are not equal to each other, then it couldn't be based on some single function, right? What we're working with could not be the derivative of, or the gradient of some former function, because if it was, those two things would match. Okay, so that was a very roundabout way of explaining what I'm trying to explain to you, but here it is. So f of xy equal to m in the I direction plus n in the j direction is a conservative vector field, vector field if and only if, IFF, if and only if, or if you prefer, you can do the biconditional, if and only if the partial derivative of n with respect to x is equal to the partial derivative of m with respect to y. In other words, if nx is equal to m sub y. And that's exactly what I was trying to explain over here. But this is the idea. So this is our condition for a conservative vector field. If this bottom line is true, then there is a potential function. There is some little f function, little f of xy, such that if you took its gradient, you would get f. That's the idea. And they're very, very useful because there's so much uniformity going on with them. No matter what direction, what path we choose to integrate across from point A to point B, no matter how we do that, we're going to get the exact same value, because the work done to move something in a vector field, in a conservative vector field from point A to point B, is the same no matter what path we take. So conservative vector fields are very nice, they behave well, and we like them. So let's do a quick example here to determine if a vector field is conservative. So example, is the vector field conservative? It's a very simple test. We just take the partial derivatives. So suppose I've got f of xy equal to x squared y in the I direction plus xy in the j direction. Okay, now this is a biconditional. So if it is such that the partials match, it is a conservative field. If it is not, if they do not match, it is not a conservative field, period. Okay, so this is a nice little test. It gives us a definitive answer. So this is my m here. Let me get another color for contrast. This is m, this is n. So we're going to take our partial derivatives. So we want m with respect to y, because remember, if f exists, if there's this little function, a potential function, if the potential function exists, then this is actually equal to f sub x, so we need the partial fxy. Okay. Okay, so that's if it exists. I'm not saying it does, but if it does, that's what we're looking at. So this is going to be, let's see here, just x squared. Okay, so it looks like it's not going to be a conservative field. Let's keep going. Let's check in. So I want to go in sub x. So remember, if there is a potential function, this is f y x. So this is going to be equal to y. Meant to go back to the other color. There we go. Y. Well, x squared is not equal to y, therefore m sub y is not equal to n sub x. Therefore, this is not a conservative field. There is no potential function such that the gradient is equal to this. Okay, now let's look at one that is conservative and see if we can find its potential function. So example, find the potential function for, okay, we have f of xy equal to 2xy in the I direction plus x squared minus y in the j direction. So we can verify that it is in fact conservative. So this will be my m, grab another color, there we go. This is my m, this is my n. So m sub y, this is already, if there is a potential function, m is the partial derivative with respect to x. Okay, this is going to be equal to 2x. N we want with respect to x, because if the potential function exists, n is the partial derivative with respect to y. So we take the partial derivative with respect to x and we get 2x. Then we have that my is equal to nx, therefore it is conservative. And if it is conservative, there is a potential function. So how do we find that? Well, it's actually pretty straightforward. We just integrate with respect to the individual variables. So f of xy exists, and we have m is equal to the partial with x, and n is equal to the partial with respect to y. So we want to find our function. So f of xy is going to be equal to the integral of m dx, which is going to be equal to the integral of n dy. So let's fill those out. So our integral of m, which was 2xy, with respect to x, and our integral with respect to n, which was x squared minus y. We're going to integrate that with respect to y. Okay, so integration with respect to x here is going to give me x squared y. X squared y. There it is. Plus maybe a constant function with respect to y. Okay, and over here, we integrate this with respect to y, we get x squared y minus 1/2 y squared plus some constant function with respect to x, or constant function of x. I should have called, let me call this one c2, and I'll call this one c1. They are not necessarily the same function. Okay, well, whatever they are, we know that they have to be equal to each other. So we've got our x squared y, right? There is no function of x over here, so we know that this is equal to 0. Allow me to elaborate on that. On the first integral that we found, we had x squared y plus some constant function with respect to y. Okay, there is no function value here. There is no part of this function, no term, that's the word I'm looking for, that is x only, right? Every term over here contains a y. So there is no constant function of x that does not also contain y. So that's going to be equal to 0. Now, looking back in the other direction, I'll grab another color here. If we look back in the other direction, I've got some constant function, some function of y only. There's no x involved there. Well, here, that's negative 1/2 y squared. And so what we have then, if we put all that information together, is that our potential function f of y is equal to x squared y minus 1/2 y squared. And how do you check it? You take the partial with respect to x, make sure you get m, take the partial with respect to y, make sure you get n. And in this case, we certainly do. But shame on me for not saying this. There could also be just a regular linear constant, right? It could just be some constant value that was attached to it, and because we did do an integration, we have to account for that. So that's shame on me. That was my bad. We will add just a constant c in here, and that is not a vector. This is not a vector valued function. It's just a regular function of xy. All right, and as with all good things in Calculus 3, this can be carried on to 3 dimensions. So let's look at the test for conservative vector fields in space over a region Q. Okay, so nope, too hard to read on the black. Let's get white up here again. Okay, so a conservative vector field test in space. Okay, so now we have our f, which is f of x, y, z, which is equal to m in the I direction plus n in the j direction plus p in the k direction, right? So three-dimensional. It is conservative if and only if, nope, back that train up. Conservative if and only if the partials with respect to one another match up. So the partial of p with respect to y is equal to the partial of n with respect to z, right? So that's going to give us our mixed partials containing y and z. Those are going to match. Our partials the partial of p with respect to x is going to be equal to the partial of n with respect to z. So the mixed partials x, z are going to match. And then n with respect to x is equal to the partial of m with respect to y. Our xy partials are going to match. So this is basically saying that the zy matches the yz, the zx matches the xz, and the yx matches the xy. Okay, all the partials, all the mixed partials have to match if that's the case. Okay, now I'm going to go ahead and throw this out right now just because we're about to talk about it, but it's also true. Also, we know that this function value is conservative if, and only if, let me write this down, conservative if and only if, or IFF, however you like it, if and only if the curl of f is equal to 0. Now we haven't talked about that yet. We're going to talk about that in just a moment. Curl of f is equal to 0. Okay, so this is a nice little caveat, so we don't have to check every single thing. We can just check the curl. Okay, so it's basically the same thing as saying this is true, these partials are true, because the curl is defined by the difference between these partial derivatives. Okay, so let's go ahead now and define the curl of our function. The curl of a vector field. Okay, so the curl of f of x, y, z is equal to the differential operator crossed with f of x, y, z. Okay, and what that is, it's exactly this. We are going to get the partial of p with respect to y minus the partial of n with respect to z. That is our I component. Minus, okay, the partial of p with respect to x minus the partial n with respect to z. That's our j component. Okay, so you can see the cross product appearing here, plus the partial of n with respect to x minus the partial of m with respect to y in the k direction. Okay, so this is the definition of the curl of a vector field. Okay, so what is the curl? What are we even talking about here? Well, first of all, it only applies to vector fields in three-dimensional space. It doesn't make a lot of sense to have a cross product of this in only 2 dimensions, because we'd zero it out. Because it would be only in 2 dimensions, it wouldn't be going anywhere else. But the curl is talking about how is that changing relative to the plane that it's in at that moment. Okay, so we're talking about how, is it bending down, is it bending around, is it bending up, something like that, right? So it's going to be changing outside of its plane. So if we're stuck in 2 dimensions, it's always going to be zeroed out. And that's a good point. If the curl of f is equal to 0, f is said to be irrotational, right? It's not curling, it's not curving around. So one more time, here we go. F is said to be irrotational. Okay, so now that differential operator, if you need to think about crossing the differential operator with something, think of it as this. Think of the differential operator as being the vector, the partial with respect to x, the partial with respect to y, and the partial with respect to z. Okay, then if you're crossing that with f, which is, undo that. So if you're crossing this with f, which is the vector, well, here, I'll just write it down. We're getting the partial x, partial y, partial z, right? And we're crossing that with m in p. Okay, so that's what's going on there. So we're taking the partial derivative of m with respect to x, the partial, and we're putting that into our cross product. Okay, yeah, clear as mud. There you go. If you have questions about this, please let me know, guys. I realize that I'm not doing the very best job of explaining, but I'm trying to give you a better intuitive idea of what's going on. For some really good details, see your book or see the Paul's online notes. I put a link to that page in this section as well. Okay, so there's one more thing in this section that we need to talk about, and that's divergence of a vector field. So the curl is a vector field in and of itself, right? It comes out a vector, so it is a vector field. So that's curl, that's a vector field. And the divergence is its scalar counterpart, if you will. So the divergence is a scalar function. Okay, so what is divergence? Well, divergence is a measurement. It's going to give us an idea of what's going on at that point or at a source, right? So if we're talking about velocities and we're talking about moving particles, maybe it's a measure of the rate of flow of these particles or fluid or whatever it is that we're dealing with, how strong a gravitational field is around some particular point, that kind of thing, but it is a scalar function. Okay, so let me go ahead and define this. I'm going to define it in the plane and in space at the same time. So it is going to be a dot product. That's what yields scalars for us. So the divergence for, oh, I should have written that down. Let's get out of there. All right, so the divergence of a vector field is given by this div for divergence of f of xy. Okay, this is going to be equal to the differential operator dotted with f of xy. Okay, and this is just going to be the second partial derivative. So m is going to be taken with respect to x, so that's the second partial with respect to x. N is going to be taken with y, so the second partial of n, the second partial with respect to y is what we're going to get here. So this is equal to the partial of m with respect to x plus the partial of n with respect to y, or m sub x plus n sub y. Okay, so that's in the plane. Should have written that down. This is in the plane. All right, and then in space, same thing, exact same thing. We're just going into 3 dimensions. So the divergence of f of x, y, z, that's going to be equal to the partials. Well, it's going to be equal to the differential operator dotted with f of x, y, z. Okay, and that's going to be equal to the partial of m with respect to x, the partial plus the partial of n with respect to y, plus the partial of p. Whoa. Try that one more time. Partial of p with respect to z, or the, second partial derivatives here. So m with x plus n with y plus p with z. There we go. Okay, so essentially, if this came from a potential function, right? M is the first partial with respect to x. We're taking that next partial with respect to x. N partial with respect to y. We're taking that with y. P partial with respect to z. We're taking that with z. Okay, so there you go. And this is our divergence in space. Okay, and if the divergence is equal to 0, it's said to be divergence free. So divergent free if the divergence of f is equal to 0. Okay. All right, and it is a scalar function, so if it comes out to just be 0, then it's divergence free. Okay, and we have one last theorem, divergence and curl. So let's go ahead and write this one down. Divergence and curl. Okay, if our function, our vector field f of xyz is equal to m in p, okay, if this is a vector field, and m, n, and p have continuous second partials, then the divergence of the curl of f is equal to 0. Okay, now that's m, n, and p having second partials. So if we were coming from a potential function, it would technically be like the third partial for us from the potential function. So if m has continuous first, m, n, and p all have a continuous first derivative, mx, m, n, y, p, z, and then the second partials are also continuous, we have the divergence of the curl being equal to 0. Okay, so that one's going to wrap it up for this section. If you do have questions, as always, please let me know.